ways of the Force and become a Jedi like my father.
Okay, so our goals in this one is we want to be able to draw the magnitude and direction of all forces that are acting on an object. So, as we looked at in our lab, there's often more than one force that's acting on an object. If you were to look right here, there's a force that's exerted downward, that we said is the force of gravity, and there's also a force that's exerted upward, which counterbalances out so that he's not falling down. So we want to be able to draw the magnitude and direction of all those forces. We want to be able to do that. This is called a free body diagram. Okay, it's called a free body diagram. And then we want to be able to relate these things right here back to Newton's second law of motion so we can do some calculations. So we're going to take a look at it. We say that most objects experience more than one force. In fact, most often they're going to experience at least two. There are some certain situations where it's going to be one force, but most often it's at least two. You take these multiple forces and you combine them in vector addition to get what you call the net force. The net force is considered to be kind of like a total force. Now, it doesn't necessarily mean that you add them all together, because if you have one force pushing right and a second force that's pushing left, well, you can't add those together because they're in opposite directions. So instead, you have to use what's called vector addition. Now, the net force has to include both magnitude and direction because it is a vector. So it is very, very, very important that whenever you do this, that you actually specify and say the force is 10 newtons to the right, or to the left, or up, or down, or something like that. Now, whenever you look at these multiple forces, we always start off from the center of the object. So we take our object, and we say, okay, here is the center of the object. And you actually draw all the forces out from that center point. So, to be fair, these things should all be connected right here by lines, kind of connecting them all the way to that center point. You're not supposed to just say, oh, okay, well, here's a box, and right here there's a force going this way, and then here there's a force. They have to be connected with that center point, because it's the center point that all the forces act on. Now, when you have all the forces, and they all cancel out. Now, that doesn't mean they all have to be equal. It means they all cancel out. For example, the left force cancels out with the right force. And then you have the up force cancels out with the down force. You have what is called a balanced force, or more often it's called equilibrium. This equilibrium term can result in two things. Now, if you take a look at this, that's just Newton's first law at work. Newton's first law says if there's no external forces, no net external forces, the object is going to either remain at rest or remain at its constant velocity. That right there is just stating Newton's first law again. Now, when you have an unbalanced force, okay, when you have an unbalanced or a net force, or if you say, hey, this force left actually didn't cancel out the force right. Instead, what we did is we said, okay, this part cancels out, but what I have is I have a leftover force right here that doesn't. Whenever you have an unbalanced or net force, that means there has to be some sort of acceleration. A couple of key forces. These are the forces that are almost always present in the situations we're going to deal with. And the first one is gravity. If you are on the surface of the Earth, there is gravity. Gravity always acts down on us while we're on the surface of the Earth. Now, if you're floating in space and here's Earth, and you're over here, well, guess what? That means that it's no longer acting down, it's acting towards the Earth. Okay, so the gravitational force is the mutual attraction between masses, and for almost every situation, it's going to be the downward force. We signify it as an F sub g. If you look, all of these are an F and then a sub letter. It's a subscript letter. Just letting you know they're all forces first, and then they're descriptions of the forces that come with it. Now, applied force is a push or a pull. It's, you pushing a box, an engine pushing a car. It's any sort of applied force, which means it's a push or a pull by something else. The normal force is the force that's exerted by the surface. So, like if you take a look at the examples that we had before, we said, okay, there's a box that's on a table. Why doesn't the box go through the table? And everybody says, well, the table's in the way. Well, that's true, but you have to go ahead and say, okay, well, there's got to be a force exerted by the table upwards. And that is what the normal force is. It's the force exerted by the surface of an object. And then last, you have this frictional force, which is a force that resists motion. And we'll get more into friction in the next lecture, but just realize that it's something that goes against the applied force, generally speaking. It's always going against the motion of an object. Now, you can have other types of force. Okay, there's things like the buoyant force, the drag force, all these other forces that we're not really going to talk about in this class so much, but you can indicate any other sort of force by just defining the letter. You can say F sub Q if you want, and you can make up a force for Q. And the free body diagram is what you say when all the forces are labeled. It's very, very, very important that these forces are labeled, okay, and that their arrow length is proportional to the force. So if I wanted to say that these forces are equal right here, but I drew the normal force way up here, well, when you look at these, this arrow is clearly longer than this one. So when you look at this free body diagram, it looks like the normal force is greater than the weight. So it's really important that you draw the arrow length proportional to the force. And you can actually use these free body diagrams to calculate the net force, and we'll get into that here in just a second. But it's very, very important that you be very careful in describing these. So, like, let's say these are close, and I'm not really sure if the normal force is greater than the gravitational force. A lot of times it's helpful to actually take Fn and write equals Fg. And that lets just anybody who looks at this free body diagram know that that's what I was expecting. I was trying to show that the normal force and the weight were actually the same number. Okay, and this question says describe the motion of the object based on the free body diagram. So if you were to take a look at this, let's look at the force up and the force down first. So if you draw this and you draw this, those are the same length. So what we can say is that the force upward and the force downward cancel each other out. So what we can say is, okay, force upward, force downward, cancel out. That means that it's not accelerating up or down. That does not mean that it's not moving up or down. It still could be falling, or more than likely it's probably just staying still, but it could be falling or moving upwards based on the forces. It just means that it's not accelerating up or down. Now let's take a look at the forces left or right. Left and right appear to be the same. So all we can say based on the free body diagram is that the acceleration is 0. Well, there's two different situations in which the acceleration is 0. When the object is at rest, or when the object is moving at a constant velocity. So now, rest is a perfectly valid option here. So we're going to go ahead and box that and just say, okay, that's perfectly valid. Now, moving at constant velocity is not perfect at this point because moving at constant velocity in one direction. Okay, it's not really the normal force because the surface is not going to exert a greater force than the weight, generally speaking. It's not going to be to the right because if the object is moving to the right, friction always opposes motion. So the only other valid answer at this point would be moving at a constant velocity to the left. In other words, in the direction of the applied force. That's the only other valid answer in this case. Let's just draw the forces acting on a rocket accelerating upward towards the International Space Station. So what I want you to think about while you do this is, what is the upward force? Be careful when you label it, because what is it that's actually moving the rocket upward towards the space station? You should be able to draw a free body diagram for a drop of water in free fall, and you should be able to do that without any help. The actual correct answer in this case would be this. Revisiting Newton's second law. So we talked about Newton's second law already, and we said, okay, Newton's second law says that the net force is equal to the mass times the acceleration. And we kind of skipped over this whole idea of net force. But now that we know there's multiple forces that are acting on an object, we know that we actually have to find the combination of those forces and say, okay, now that's my net force, and that equals the mass times of the acceleration. So we have this total force right here that we're talking about. It's a combination of all the pushes and pulls that are acting on an object. Mass is still mass, acceleration is still acceleration. Same units, same measured by, same definitions. The only difference is now we have to combine them to solve for this net force. Well, we see that in this example. Example B1. It says, determine the acceleration of a truck based on the free body diagram below. And it looks like I don't have a whole lot of information at all. So remember, the two ways that we can find acceleration is we can use if that, which is our kinematics motion equations. And in this case, I've got no information on velocity or distance or anything like that, so that's out. And our other way that we can solve for acceleration is F equals ma. Now, based on the fact that I have a free body diagram, it looks like I can have some sort of combination to solve for this F term. And I do. And also, if you remember the relationship between weight and mass, you should be able to go ahead and figure out what that is as well. So we take a look at this. We say, okay, what is the net force that's exerted on this object? So we're going to take a look at the up and down forces to begin with. And I've got 80 newtons up and 80 newtons down. So those cancel each other out. They're gone. Now, whenever you do this with the left and right forces, you can see that 100 and 20 don't cancel each other out perfectly. But what I can do is I can say 100 minus 20. The reason why I would subtract is because they're in opposite directions. Now this 20 is gone, and what I'm left with is 80 newtons to the left. So that's my net force right there. So now I have a net force of 80 newtons equals some number A. So the trick to this particular question is saying, okay, what is going to be the mass? And in order to figure out the mass, remember you got to look at the relationship of this weight. We've said that before, that the weight is equal to the mass times the gravity. So I have the weight as 80 newtons, and we can say 80 equals the mass times gravity. Just for simplicity reasons, we're going to go ahead and say that gravity is 10 in this particular case. So whenever you do that, you can solve for the fact that 80 divided by 10 gives you a mass of 8. You can then take this mass, and you can plug it into our equation, and we have 80 equals m times a, where our m value is 8. 80 divided by 8 tells you the acceleration of this object to the left is 10 meters per second squared. Okay, a hint on this example B2, it says a 10 kilogram box is accelerated on a frictionless surface at 2 meters per second squared. Draw a free body diagram for the box. So you should be able to take the mass here, and you should be able to figure out what the weight and what the normal force are, and then you should be able to take the mass and the acceleration and be able to solve for what the force is to the right. Now this term right here also tells you what friction is, so you should be able to draw that on your own. On this one it says a person is capable of pushing a car to a gas station. They're capable of pushing with a force of 100 newtons, but only manages to maintain a constant velocity. Use a free body diagram to explain what must be occurring. So I'll go ahead and draw it, and you should be able to justify what this is as the answer. So we have a gravitational force, a normal force, an applied force, and we have a frictional force. And what we can say is the applied force equals the frictional force, and we can say the normal force is equal to the gravitational force.